This is the last part of the lecture I wanted to do. I was planning to do it in the morning today, but we'll do this quickly now. And so, because I wanted to finish up with the large-scale picture of observational astrophysics, basically, because we've been talking about, like in the beginning, we talked about cosmology and galaxy formation. Then we talked about observing galaxies, observational techniques. Then we looked into simulating things like simulating stellar populations. Then we kind of matched data with the observations. Now it's just like a summary of the things to look into how we have used these kind of techniques to improve our understanding of the galaxies in the universe by you conducting different surveys, because the data, for example, what you use today comes from one of the surveys, and there's many of these surveys that has been done to study the evolution of galaxies in the universe. So we'll talk a little bit about the history and then what the future holds as well for us. So in the beginning, people were thinking what galaxies were. So there were like a lot of different ideas floating around. And in the ancient days, there were like they worked out how the planets or like stars revolve around the Earth, for example, in these geocentric models. And you can see, like in the Asian cultures, there was the horoscope ideas where you knew, like mathematically very well, how the stars moved around the cosmos, for example, within our in a more mathematical sense. So what is a galaxy? The first thing that people thought was that they were like distant universes kind of a thing. That was what Immanuel Kant thought. And then like Messier, of course, looked into a lot of these nebulous, he called it like gaseous nebulae, in the universe, and he categorized around 100 of the 110 of them. And later on we found that they were not just nebulae, but they were compilation of galaxies, star clusters and other things together. And we still use the Messier numbers, the M numbers, M51, M87, etc. comes from his catalog up to 110 or something like that. Then William Herschel was the one who actually did a lot of service to making telescopes and stuff, and he did a lot of observations as well. So, but we didn't really know galaxies existed until the 1920s, because people thought that everything that you saw in the sky was a part of our own galaxy. And even the Andromeda galaxy, when they observed from the telescopes, the first idea was that it is kind of like a gaseous nebula which lives around within our own Milky Way. And now we know, like, it's our closest companion to us, living around 2.5 million years away. And this might be the only galaxy that we have observed to identify individual stars, etc., in greater detail. So Edwin Hubble's work helped a lot to understand that there is something called galaxies, because we looked into Hubble's law last time on Monday and some. So we understood that these things go far away with distance. The speed increases, so this kind of made the baseline to understand that there is something beyond our own Milky Way, and understand that we are just only one galaxy in the large scale cosmos. So that allowed us to define something called the local group. So there is the collection of galaxies within our own Milky Way. And there is a lot of studies going on to understand galaxies within our Milky Way around us, understand how the merging and other things happened in our galaxies. And with more surveys happening, observing in different conditions, we developed Hubble's diagram into more detailed versions, dividing between spirals, barred spirals, and looking into very, very different scenarios, and we managed to push it further into beyond the local group to look into very distant universes, very distant galaxies, and divide them into spirals, for example, and like we have like elliptical galaxies, we have irregular galaxies. So like the surveys kind of improved our understanding of galaxies in many different ways. So if you want to do statistically significant studies of galaxy evolution, it is really important to do these kind of surveys, because then you observe up to a certain mass or magnitude limit. And completeness is a really important thing in astronomy, because when you observe something in the sky randomly, you are more likely to see something which is an outlier, because you will see the brightest objects first. So you need to do like very complete surveys of the universe to understand the general population of galaxies, and then supplement these with spectroscopic data when possible, and understand galaxy evolution. So there are two different types of galaxy surveys. One is like all sky surveys. These are shallow but looks into the whole night sky. So like these doesn't really go into high redshifts. Then if you want to study high redshift galaxies, you would look into these deep surveys where you'll point a small part of the sky, but you integrate for a longer time to get something like a pencil beam out. All right. So one of the first large surveys was this thing called the 2-degree field galaxy redshift survey, which took spectra for around 250,000 galaxies, covering like a large portion of the sky. And because we knew the distances from spectroscopy to these galaxies in finer level, it really helped to understand this filamentary structure of the universe, to understand how the cosmology works within our close to our Milky Way, the near field cosmology. Then afterwards came the Sloan Digital Sky Survey. I'm pretty sure you probably heard about these as well. So this kind of completely revolutionized our view of the universe, because it obtained observations of the whole northern sky in some sense. And so far there's about 100 million galaxies observed from SDSS, and it's still going on project focusing on specific cases. And there's more than 1 million galaxy spectra complementing it. So there is a lot of data available in the low redshift universe, going into finer details, so you can do very statistically significant studies of galaxies. And more recently, in the southern hemisphere, there was a survey called the Gamma survey done, and it obtained spectra for around 300,000 galaxies. And it is also getting supplemented by a survey called the SAMI survey, which is observing using an IFU. And if you remember from the second day, an IFU is an object that can take the image and the spectra together. So you're getting more information out of these galaxies, and there are more massive surveys planned. And from surveys like Gamma, we were able to construct how the 3D structure of the universe, because now we have the spectroscopy as well. From the images, now we will know exactly where these galaxies lie, and then try to understand how these things are linked together, and how this large scale structure of the universe formed at different times. So this is just one of the fly-throughs made from the observations from the Gamma survey, showing how the galaxy structure is in one part of the southern sky. And from the surveys, there has been a lot of important results coming out, because now, as I mentioned, we can do studies in more statistical methods. So we figured out how the star-forming galaxies are different from the quiescent galaxies when you look at different colors. And then we try to understand how galaxies evolve and how the galaxies stop forming stars. We looked into the IMF of galaxies in more detail from SDSS and also from Gamma, for example, looking into finer details. We found galaxies which would have not been found otherwise, like these low surface brightness dwarf galaxies, because we now have a more complete sense of the of our sky around the low redshift. So there has been a lot of science that has happened from these low redshift surveys, which has compiled a lot of galaxies. But that's not the only thing. As I mentioned, there are also surveys that tries to look into the very high redshift universe. And so what you do is you observe a small patch of sky, but then you go very deep. So you call this something like a pencil beam like a structure, because a pencil beam is very thin, but it is very long, right? So you're looking into the early stages of the universe by integrating longer and longer. You can't do like large scale sky coverage, because if you want to go deep, you have to expose for a longer time. And this was kind of like a new step was taken from this Hubble deep fields, which what Hubble did was it looked at blank patches of sky. So it happened in the early 2000s in the beginning, where the director decided that he needs to do something with the time. If you're a director of the Space Telescope, you have like a specific time for your use that you can decide to give to anyone to do science, basically. So you don't have to go through any kind of formal like competitive processes. So he decided, okay, let's look at the look at a piece of the sky which has no stars, nothing, very black patch, and then he observed for a long time. And afterwards, this image of the Hubble ultra deep field came up. I will show you next. And it was the first thing that people realized, that even dark patches of sky contains millions of galaxies that we cannot see. And that is why they understood the importance of doing very deep surveys. And afterwards, a lot of different regions were observed, Cosmos, Good South, etc. And the data that we use today for some of our work was a part of the Cosmos pointing as well. And all of these HST fields were complemented from a lot of ground-based surveys as well. And because HST only has specific bands, and to go to like, so you do a lot of optical follow-up studies of this. And surveys like Candles, Relics, and Buffalo, you can look it up later on. These are like some of these surveys. For example, Candles observed in almost all of these fields, for example, taking very deep images in many surveys. So like this is an, should be a video actually. Yeah, so this is a video of the Hubble ultra deep field made by photometric redshifts. So similar to what we were doing today. And so this was a blank patch of sky. It was a complete black thing without anything at all. And you can see how much structure was found out when we looked into this thing using Hubble. So like it opened up a new era of galaxy evolution, basically. And you can do the same thing and fly through the thing to go to the most faintest galaxies in the universe. But apart from doing very deep surveys, there is also methods of increasing the efficiency. And one thing is called galaxy lensing. And has people heard about what galaxy lensing is? Gravitational lensing, yeah. So because if you have a very massive object in the universe, because of Einstein's general relativity, he explains that the space-time is bent, and that means it can act as like a magnifying glass. So for example, this picture that you see here is one such cluster. It is a very massive cluster, and if you observe deep into this cluster, you can see things behind the cluster getting magnified in different levels. So you can probe the galaxies in the very early universe in a more efficient way. But the only problem is you're looking into a very narrow piece of the sky, but it gives you a new view of the universe because it boosts the signal, as you see. So you have the cluster in the foreground, which bends the space-time idea, and that acts as a lens. So you can observe these very faint galaxies in the very early universe, redshift 7, 10, for example. The higher redshift we have is redshift 11 so far. So you can see like how deep we can go from these lensing kind of structures. And there are new fields, like for example the frontier fields is one of these surveys which observed around 140 observed with Hubble, and which went deep in different cluster regions to observe the galaxies. So this is one just example of a pointing where you have the cluster in the middle, and because Hubble has two, you can observe in parallel with Hubble, okay? So you have a lensing field, and without wasting time, what astronomers did was you observe the second part of the instrument which can be observed together in Hubble to a blank patch of sky afterward. So if you look into some in the internet, you will find that there's Hubble clusters, lensing clusters, and lensing parallels. And because of that, you got like very deep images of more complementary blank patches of sky, and also with lenses. So for this survey, did like 6 different clusters, and you need to do a lot of these surveys because the cosmic variance is really important to account for, especially at high redshift, because if you're looking at a very small patch of sky, you're going to be biased. So you need to do multiple pointings to remove the effect of bias in cosmology. So you observe for around 840 orbits. And apart from Hubble, there was also the Spitzer, there is still also the Spitzer Space Telescope, which observed in the infrared part of the spectrum. And it also like observed deep photometry, like for example the GRADES program, which observed 732 hours pointings in the good south and the north fields. So they got very deep exposures in the infrared, and so images like this from Spitzer was also is in the catalog that you use. So if you look into the .cat file, there is also like data points from Spitzer as well. So you go into the infrared part of the spectrum. From after photometric surveys, spectroscopic surveys are also very crucial to understand information about galaxies, because that will be helpful to know exactly where the galaxy is, and to understand the emission line properties of galaxies. If you want to know like elemental abundance in greater detail, ionization parameter, etc., as we tried up some of these things in the models that we computed, we need to get observed spectra of galaxies as well. And the MUSE instrument that I mentioned like a couple of days ago was also like has helped to revolutionize our view of the universe, taking spectroscopic data. And for example, in the UDF field that you saw before, how the MUSE also did like a deep pointing of 30 hours complemented by 10 hours of around it, and it got more than 1,000 galaxy redshifts. So 1,000 at high redshift is a very big number, because you had about like about 100 or something in the past. So by just one single program from MUSE, you managed to increase it by almost an order of magnitude. And there's also a program going on in MUSE to observe a patch of the UDF up to 160 hours. It's almost half done now. So once it's completed, it will be the most deepest pointing in the universe so far done. And you will have spectra, don't forget, for each of these points in the pixel from MUSE, right? So you're getting all the deepest image plus the spectra at each single pixel. So you're going to get a lot of information out of these systems. And this is how you try to push this our barriers that we have observationally using this new generation of instruments. So this is a new fly-through from the MUSE survey of the ultra-deep field. Now the redshifts are fully accurate, and you can see more like extended structures from Lyman alpha, etc. And you can again zoom through this region of the sky. And you can see now the structures are more defined, because you know exactly where these objects are, and you can get, and for all of these galaxies, there is also like redshift and spectral information. So you know what is their compositions, what is their star formation, and all the other details as well. And so let's, all right. So apart from MUSE, UDF, you can also go to the sub-millimeter range. and that is what the ALMA observing programs are doing. So ASPEX is one of these programs which are taking sub-millimeter observations of the MUSE region in sky in the UDS, and this telescope is one of the largest, I think this is one of the most expensive, largest telescope built on the ground, and it's in Chile in the Atacama Desert, and it's like a massive field of antennas, and you're observing in the sub-millimeter range in the universe. So you can push the galaxies into the fainter universe, redshift 7, 8, 9, 10, 11, and you can also observe like the neutral carbon and neutral carbon monoxide, oxygen lines, etc., which is very useful to understand how star formation happens and how the gas cools in the galaxies and gets recycled into forming stars. So this is kind of will show us the fundamental physics behind the galaxies, and by combining it with optical data from MUSE and then from the HST pointings, you can see like this patch of sky is getting very multi-wavelength coverage as well. So this is the surveys that are going on so far, and then in 2021, hopefully the James Webb Space Telescope will also come online, and it will be on the L2 orbit of the it will get pushed very far up. And let me play this again maybe so you didn't miss it. So that means this will be like very far away from us, orbiting around the Earth. The orbit is beyond the orbit of the moon, as you see here. So it's orbiting very far away in this L2 orbit, so it's important for infrared telescopes. And this is the largest space mission undertaken by the humans so far, because this mirror is like 6.5 meters, so they had to specially develop technologies to be able to make it fly up. And there were a lot of delays, but hopefully by 2021 it'll get run. So this is just a size comparison. If you have someone, I don't know who Sylvia is, but like a human, and then you have the Hubble Space Telescope, which is 2.4 meters. And then you can see the difference between the James Webb Telescope, which is coated with gold as well, like 6.5 meters. So, and the advantage is we're observing in the infrared as well, near infrared. So you're gonna get a massive collecting area compared to Hubble, and so far you can see the depth image quality we've got from Hubble, and you can imagine what we're gonna see from James Webb Telescope, because it's gonna be bigger. And also it's going to observe in the near infrared. So that means you're going to push the redshift to redshift 15 or even 20, because all the lines that you see in Hubble will get redshifted into the near infrared. These are the rest frame optical lines will be in the near infrared at high redshift, and that is why it's important to push this redshift barrier. And these are some of the instruments in the James Webb Telescope. You have the NIRCam, which is an imager that I think some of you did calculations for this on Tuesday. There's also NIRSpec, which is a spectrograph with the same wavelength coverage. There is NIRES, which is like a slitless spectroscopy. So you do you can do spectroscopy using prisms in this one. You're gonna get spectra for all the field of view. And also there is a mid-infrared imager, which is going to go up to like 25 or 30 microns as well. So you're going to get a lot of information out of these from these instruments, because for example the H alpha line, the main star formation line that we can observe from the Earth, the limit is redshift 2.7 for our atmosphere. Anything beyond that we can't observe, because that line is getting absorbed from the atmosphere. So you have to go to space. And with the NIRSpec, for example, you can push that up to redshift 6. So you can observe the prime ingredient for star formation up to redshift 6. And with MIRI, you can further push it down as well. So you can see like we're going to get a wealth of information from spectra, and that's going to be really, really useful. So just like a small view of what NIRSpec is. It was built by US, etc. So just for completeness to get an idea. Then you can see how they improved the NIRCam, how the technology improved with time. For example, NICMOS was the first near-infrared imager that you had in Hubble. Then the WF3 came online. So these are some of the data that we use today was from this pointings from this instrument. And now we are going to go like into a much larger field of view, twice of that, using NIRCam into the higher redshifts. Because HST is an instrument that is artificially heated up to keep, because this was built ages ago, like you need to heat it up and you can't observe in the infrared because of that. All right? And then you have the NIRCam compared to the Spitzer, like how you're going to get more than 1,000 times better improvement of image quality. And like a small area, but it's going to get very good image quality from this imaging from James Webb Telescope. NIRSpec is a spectrograph, as I mentioned before. There are slits that can be configured. So if you have an pointing like this, what you will see is something like this. Because for each slit that is there, you will get a spectrum for the galaxy. So you get a lot of information out of it as well. This is how they were building it in the things. And so this, the technology they put is something called the micro shutters, which can be opened and closed electronically, because in space you can't fix anything. And the problem with James Webb Telescope is that once you send it to space, it's gone. Like there is no way to send humans to fix it because it's too far out and you can't sustain anything there. So that's why they want to be extremely careful that everything is perfectly fine. And that's probably one of the reasons for the delays as well. And you can see that these surveys will push the boundary so far. For example, you have the surveys that has been done with Keck and Gemini so far, which goes up to about 10 to the minus 16 in flux limits. And when you have NIRSpec, for example, you can go like for these Webb 10 to the minus 18. So you're going to push further and further down to get the most faintest galaxies in the early universe from these telescopes. And of course, MIRI is less sensitive because when you go into the far infrared, it's really hard to make sensitive instruments because heating and other things matter. But it's also pushing from speed, so you can see like the improvement in quality of the images. So this is for space, which is getting built. And of course, I mentioned about one of these 30-meter class telescopes. And one example is the European Extremely Large Telescope, which will be having the first light in 2024. And this is a plain size compared to that. I actually managed to find a video in subtitles in Spanish, which kind of, I don't know what it explains because I didn't have time to look into it yet. But it explains the ELT basically. All right, so that's, I don't know, yeah, I think I got somewhat meant, but anyway. So there is 3 instruments coming on the ELT as the first light instruments, the Mikado, Harmony, and Mosaic. I think you worked on Mikado on the first day, if I remember correctly, right? Some groups maybe, okay, yeah. So these are imaging, spectrographs, and IFUs and other things. So like it's going to be like very large, deep surveys in this optical and infrared regime for these galaxies, these telescopes. And of course, there's also the radio wavelengths, which I have been ignoring completely for the whole of this workshop because I don't really work on it. But there's KA, for example. I will show you another video of it, which is going to be like a whole square kilometer of radio antenna. So it's going to be the biggest telescope ever built. And that's going to observe galaxies to this 21 centimeter line, for example. So it's going to be like we're going to learn a lot about how galaxies and the Big Bang and the evolution of the universe in much finer detail using radio telescopes. Because if you remember from redshift, like you need to go into longer and longer wavelengths to observe things in the early universe. So this is a video done for the square kilometer array, and just shows you some simulated view of what the place would look like. Yeah, so this is the New Zealand part of it, and it's going to get built in 2 different continents. Half will be in South Africa, and the other half will be in Australia. So this is the Australian part of it, and you can imagine it's going to be double the size because the South Africa will have half of it as well. Okay, so and not only like the imaging stuff that's going to come out from this telescope is going to give a lot of technological challenge as well. So from the data freight, for example, the SKA, it's going to be massive. Like people never imagine how big it's going to be. It's going to be in petabyte scales. For example, if you imagine how big the internet is, from if you take all the videos, all the data that exists from the 1980s of the invention of the internet up to today, if you take all the size of the whole internet that has been there, so not the ones that we have today, but if you add everything that has been there since the 1980s, the beginning of the internet, the SKA raw data, the amount of raw data made by SK in 1 day is going to be more than that. So if you imagine like it's going to be like 25 years of whole internet put together, and SK is going to make the same data level observing the universe in 1 day. So you can imagine the amount of data is going to get processed. That's why you need to have a lot of technological challenges with these kind of instruments. And a lot of people have been working hard on like how to take what you want from data in very short time periods and delete everything, storage capacities and all of these issues. So there is a lot of technological advancements happening with telescopes like this. And these are the things that are getting built, and there is planned telescopes for the future. And one thing is called the W-FIRST telescope, and this is a space telescope. Which will be has a 2.4 meter mirror, I think. So there's a story behind it. I'll tell you later. Okay, so like what happened was, so when Hubble was put to space, they made a mistake in the mirror, but so they had to send people up to space to fix it. And the thing was, after 20 years later, and for astronomers, that mirror was one of the best. Very hard, what do you call, like it was the best mirror that they ever made. It was a very big technological challenge for them at the time, and they realized 20 years afterwards that the US military had similar kind of mirrors made even before that, observing on Earth, of course, because they were looking at spy satellites, looking at spying on us on the ground. So some of these mirrors were released because like after 20 years, this confidentiality of things expires in US, so it could have been used to anything. So one of the ideas was, okay, like if the quality is going to be so great, so why don't you build telescopes out of it? So W-FIRST field of view is going to be massive compared to Hubble. You can see one Hubble pointing is this much, and with W-FIRST you can observe that big of a sky. So it's going to be a massive field of view going into the deeper universe. And this is also going to change our observed matter of the universe. But that is like one part of the things. If you know from the cosmology, you know that we can only see this small 5% of the universe from all of these observations of the universe. And the whole 95% is still almost unknown, because we don't really know what dark matter is. We don't know dark energy, for example. So there's a lot of things happening, and the final thing I want to say is that most of the interesting things are yet to come. So I hope you learned something from the science part of the things and motivated you well enough to think about doing astronomy in the future as well. And of course, the people here like Esteban and stuff are really helpful for you to help to get, probably if you want to get a career in astronomy and stuff, they will give you good advice, I'm pretty sure. And yeah, so this is all I wanted to say, and I'll stop here. Thank you. Is there any questions? No? This didn't really have much science in it, just to give you an overall view of the things that we worked on and what to expect in the future was the idea. All right, if you have any problems with the softwares and stuff, you can of course email me anytime. And my email is there on the thing, I think. Yeah.